Light is perhaps one of my favorite topics in physics. And it's one of the most fascinating, one of the most interesting things to study. And so we're just going to use some ideas that you probably already have about waves, and we're going to go ahead and apply those, and we're going to use some light, and we're going to see if that light is a wave. So who can define a wave for me? Anybody? When you hear the word wave, what pops into your head?
Goes up and down.
Up and down, right? What else? Anything else?
Energy. There's movement. There's movement and flow.
Flow, movement, energy, right? I usually associate it with surfing, like out in the ocean, right? Because I'm from the beach, and so whenever I hear wave, I'm usually thinking of water. Waves in a water, something moving up and down. The simple definition for a wave and what a wave does is a wave is just a way to transfer energy. That's all it is. One of the ways I used to transfer energy is we would, in the summertime, go swimming with my brothers and myself. And of course, we'd make huge cannonballs. You'd run in and jump and make a big wave, and the water wave would come. And then you try to time it with your other brother to jump on the other side. And you jump just to the left and right of my third brother, and then hopefully try to drown him. Right? So the waves come together, and you try to get them to go under the water. Right? Well, the neat thing about waves is that they can occupy the same region of space. And so waves can add together. You guys have all seen waves come together in a pool, and it makes a bigger area. So we're going to do some simple math here, okay? Nothing too difficult. Maybe you can help me out with this one. We'll just start off with like a wave pulse. Right? You slap the water, you see a wave leave from your hand. All right, so there's a wave pulse. Okay, here we go, some simple math. If I add those two wave pulses together, what am I going to get? Yeah, it'll be this plus this. Oh, okay. All right, we can do that math, right? All right, here we go. Let's try this one. How about that one? Can we do that one? Yeah, let's see. How about, they would add together like that, right? Yeah, when two waves come together, they over-occupy the same space you've seen in the water, you get a bigger wave. All right, let's make it a little bit more complicated. Let's have an up and a down, and then add it to an up and a down. The same region of space, what am I going to get there? Let's see, well, this one up here gave me a big one, right? Yeah?
Smooth.
Big, small. Yeah, just amplifying, right? These waves are adding together in such a way that they're getting bigger. We call that constructively. And so they're adding together constructively. Well, let's get a little bit tricky here. How about if we add a wave like this, plus a wave like this? Here we go. Now what's going to happen?
Would it be flat?
Yeah, it'd be flat, right? Because this one here has an up hump and this is a down hump. And so if they're in the same region of space, we're going to end up with anything over here. It'd be flat. Well, let's see. We call this constructive. What do you think this one is? Destructive, exactly. Yeah, so when waves occupy the same region of space, we have constructive interference if they come together and add up. And you have destructive interference if they come together in such a way that they overlap and they destruct with each other.
Nullify.
All right, well, excuse me?
I said nullify.
Nullify each other. Yeah, that's a good word too. All right, well, let's get a little bit more complicated. Instead of drawing them up here, let me avert your eyes over here to the overboard, the overhead. And Lakshmi said at the beginning that we have propagation wave. If you want to keep a wave going, for example, in the water, you're taking your hand and you put it up and down, you can keep the wave propagating. And so you have this oscillation up and down of a wave as it goes through space. And so I'm going to simulate that with a longer wave here. And my wave is oscillating back and forth, and this might be a snapshot of it, a picture of it in time. And so I have two waves, and actually I've got them laying right on top of each other. And so if I have two waves like that, it's a little bit over that. I'm going to bring the other one down here. Well, if I have two separate waves, and I have them exactly overlapping, you couldn't tell the difference. But what would happen if those two would add together? They were in the same region of space. Yeah, we would add constructively, and I'd have a wave that's roughly twice as big, occupying that region of space. If I shift the wave over, right, how about like that? Well, then what happens? Just a little bit. Are they going to add together still? Yeah, let's see. I mean, if I kind of put in a middle line right here, going across the center, right? And then I just say, well, let's see. This one's going to add, and this one's going to give me, oh, I get a bigger one there, right? So they're still adding together, right? This one and this one would add right there, right? There's still a bunch of places where it's adding together, right? And so that might be pretty complicated. It's not quite as simple as this. So let's just focus on the places where it adds constructively. It all adds together. Or if I shift this over exactly one hump, then here would be my other case. And that would be destructive interference, where every place that there's a hump, there's an opposing hump from the other way. And that would give me a flat line, because it would completely destruct. All right, so what I've done below this line here is I've just represented the humps with a solid line, and I've represented, a hump that comes up with a solid line, and a hump that goes down with a dashed line. All right, you guys have taken a rock and you've dropped it into water, and you see that it makes rings when it goes out. So in three-dimensional space, actually, the wave would be propagating out as rings, and so that's why I've arched them a little bit. And so I have solid line, dashed line, solid line, dashed line, and that represents a wave. So now, let's get back to our question. Is light a wave? Well, we've kind of described and defined some characteristics of waves. Light is a wave that propagates through space, kind of like the picture that I have here, where you have solid lines and dashed lines represented up and down parts of a wave. And so if I take two of them and I put them side by side, and I allow them to come from two different locations. And so I'm going to take a light source, and I'm going to shine it through two regions of space, so that it's like having like a light bulb here and a light bulb here. And I'm going to look for regions or areas where I have places where we can see light is adding together constructively, or it's adding together destructively and canceling itself out. Now, if it comes from two light sources, well, there it's hitting the wall. Well, they're two locations away from each other. And so let's just go ahead and arch these two together a little bit. And you can see that if I have my location on the wall, right between the two of them, you see here I draw a straight line out. And there's a place on the wall right there. I'm getting the top of a wave and the top of a wave right there. What's going to happen there? It's going to be bright. Yeah. And if I go to the right or to the left, right, well, then what's going to happen? Well, if I shift it forward a little bit and bend it down, then I'm going to get a spot on the wall that's going to give me a destructive and a constructive place, and they're going to cancel each other out. And so why don't you guys all come up here and let's see, in fact, if this happens when I shine light. Here I have, come on up over here around the screen. Here I have just a little slit, like I drew up there. It just has a little piece of paper that's got two fine little holes cut in it. And here I've got a light source, which is a laser, which gives me a single color of light. And what I'm going to do is I'm going to shine it through here, and if light is a wave, then we should see regions on the board where light is adding together constructively and destructively. And in fact, we do, right? If you look here, you can't see, get a little closer. You can see here that there's a really bright spot right in the middle, right? Which one did that represent? Constructed. Yeah, it's really bright. So that would be the center point where the two of them were coming right to the location. And then right to the side here, you see there's no light at all. That's the destructive part. And then it works its way out, and the further you get away from the sides, the dimmer it gets, because the light sources get dimmer as you go further out. And so, is light a wave? Yeah, from the simple things that we just learned about what happens when waves come together, from some of the things that we know what happens just from our everyday experience, we can do this simple demonstration to in fact show that light was a wave. Well, wait a minute. What happens if light is a particle going through these slits? What would you see on the board here? Only two spots. Yeah. So since we don't see two spots, we have to figure out why. How do you know? Why go away? That's it. All right, one of the things that we do in science is that we apply the scientific method. And everything that you interpret in nature and that you're going to deal with, you have your perception about it. In your different fields like cultural anthropology, we have our perceptions about how we view objects based upon our own experiences. Religion, people have their own perceptions about how they view the world, and they're very prejudiced about that. In science, you have to try to be non-judgmental. You got to try to just come to the table with a clean slate. And the way that we do that is through our five senses. And so what I'm going to focus in on today is I'm going to focus in on our eyes and how our eyes, the information that we receive that goes into our brain, it interprets our data, and that sometimes we can be tricked because of that. So my focus and my objective is to show you and make you aware of that, because when you bring that into your disciplines or anything that you do, that's something that you need to be aware of. And so watch me. If you could do me a favor, if you could read this for me, I would appreciate it.
Paris in the spring.
Paris in the spring, right? Yeah. This is one of the common things that happens with our mind. Paris in the spring, right? Yeah, your mind, you just instantly go over that. That's a common mistake. Let me ask you this, Laylee. At the top over here, at the top here, is that slanted line broken?
Yes.
Yes, right? You would say that it is, right? And our mind would interpret that data. We receive the information. If you notice I put a little card right along that line, you'll notice that, in fact, no, it's a straight line that runs all the way through there.
Yeah, and I thought of that also. I knew it wasn't, but it looks broken. Yeah.
Right.
It looks broken.
And what about this one here, right? Are the dashed lines shorter or longer? These dashed lines, are they shorter than or longer than those lines? They appear longer, and of course I wouldn't put them up there if they weren't in fact the same length. So in everything that we look and perceive in science, we need to be aware of these things. And so let's just start with an overview of the eye, learn some of the basics, and then go on to explain how the eye works, and then look at some of the perceptions that we receive from the eye. So I have up here some basic components of the eye. We'll briefly go through them. Here's your eye. It's composed of some major elements. The cornea, the outer part of the eye. The iris, the colorful part of your eye that opens and closes. The lens. And then the back part here is the retina, with an area just behind your eye called the fovea. And then down here, which is called your blind spot. And your blind spot is an interesting feature in your eye in that it allows you to, your brain allows you to have information there even though it might not be there. And so I want to go ahead and hand out these handouts. And what these are is they're little demonstration to help you find your blind spot. So what I'm going to do is read it through you, do it with me. If you can't find your blind spot right now, that's okay. You can take it home and practice it. A lot of people can't do it right off the bat, so I'm only going to spend about 25, 30 seconds finding it. But it says, close your left eye and look with your right eye at the round dot. Okay, so cover up your left eye and adjust your distance and find the blind spot that erases the X. And so you just bring it forward and back, and you want it in the plane directly in front of your eye. And you can bring it forward and back, and you'll actually see that X disappear if you say focus on the black spot. Don't move your eye off the black spot. That's the hard part. Stay focused on the black spot as you go. And it's probably going to be a little bit closer than further than it is away.
Mine is exactly right.
Right there? Yeah.
But the next eye is not working. I have to adjust.
How many people were able to find their blind spot? Good. Most of you can. If you can't, go ahead and do that at home later on. But in that one region of space, what your mind does is it takes the data around it and it fills it in for you. And so it's really fun to play with that. Once you find it, the exact location of it, then you put your finger there, then move your finger away, and that information gets filled in based upon the background knowledge.
Say it again.
Once you find your blind spot, okay, you can use with the sheet of paper, you see the X disappear, bring your finger into where that spot was, And then what you do is you pull your finger away, and that information that's out there, your mind is filling in. So if it's like the chalkboard color, your mind is filling in everything green. It's fun to play around with that. And so how does your mind actually interpret and perceive the data? Well, in your eye, the information is going to be received by the rods and the cones. And the rods and the cones are the cells that are in the back that are sitting on your retina. And they have different functions. The rods act as kind of lightness and darkness perceptors. They perceive bright objects and dim bright objects. And the rods are also more sensitive to motion. And we'll go ahead and do a demonstration shortly to see the difference in these. And then the cones, there's 3 types of cones, and they are receptive to different frequencies of light, which I just represented by color. Some of them are more prone to blue, some of them are more prone to about the yellow color, and some are more prone to the red color. And so we have these different receptacles in our eye where at the fovea we have a lot of color, right at the back part. That's where all of the color, we want it to be really crisp and sharp, so it's very dense with the color. And as you move around the back side of your retina, you lose more and more cones, so that when you're way out here and you see stuff out here, it's almost all rods. And so because of that, you can't tell color. We're going to do a little experiment to prove that. So what I want you to do is reach in here, grab a pen, don't look at it, just put it behind your back. Okay? Put it behind your back, don't look at it. Okay? Good. Good. Okay, put it behind your back. Here's what I want you to do. All right, lift the pen up and put it back behind your head like this. Slowly, just shake it up and down because the rods are sensitive to motion. Look straight ahead and bring it forward until you can see it, the motion. As soon as you can see the motion, stop and try to identify what color you're holding out there. In your mind, see what it is, and once you think you know what it is, pull it out in front and look at it and see if you were right. Go ahead, bring it up. You got it right? Some of you might have gotten it right. I got mine wrong. I thought mine was red.
I thought mine was
Depends on the color.
I was trying to say yours.
That's because out at the edges in your back of your retina, you have more rods than cones. And so color is hard to perceive out here. But motion is easier. Black and white is easier. I have a picture of what those look like up close in real life. You can see here these are more cone-shaped objects. The rods are more like this. A couple of other things about the eye and how you perceive. And that is pupillometrics. All right, there's an actual study of this, and it has to do with your iris opening, and we can perceive people's emotions. A lot of your emotions are tied up into that pupil. That iris opening up and bigger and smaller in the size of your pupil. And so, just a really quick check for those of you who, want to see if your husband's telling you the truth or your wife's telling you the truth, and they say that you love you. Well, and when your pupil gets really big, usually that means that the emotion is there, it's genuine. If it's small, they're probably lying to you. So that's just a quick check. Another perception that we have with our eyes is called lateral inhibition, and it's the ability for the eye to perceive bright objects and dim objects that are very, very different from each other. For example, looking at a light bulb in a black room, the intensity level might be on the order of magnitudes of millions of times brighter compared to the closet in a light bulb. But your eye will take that and it'll say all the receptors that are seeing the light bulb dim down and don't perceive it as bright. And so that's another way that your eye perceives that information. Because of our lateral inhibition, our eyes tend to look at edges and focus in on edges and perceive them to be there. And so if you look at this sheet of paper right here, you can see there, everybody sees an edge there, right? Yeah, in our mind's eye we perceive that we have 2 different colors. It looks like it's shaded differently, but if in fact I've taken a slide this pen up over that edge, what happened to the 2 regions? They're the same. So there's another area where our eyes perceive us from the information that we have. And so The last one I want to show you is in terms of timing of your pupils and show you how you're deceived in that nature. And that's how I'm going to close my talk. And so what I want you to do is stare at this spinning disc for the next 20 seconds. Don't take your eyes off it, please. Stay on it. Stay on it. Keep staying on it. All right. When I tell you to, I want you to look up at my face. Not yet. Okay, do it. Do you see anything?
Undulations.
Yeah, little undulations, right? Yeah, that's because your rods and cones are trying to catch up. And so you're asking my wife, what should I do? She was giving me suggestions, and I just struggled and contemplated trying to do something new and different. And then I was thinking out of the box. I was thinking geometrical shapes. And so I thought, oh, geometrical shapes. And it hit me, and then I saw this toy that I have, and it helps with the construction of geometrical shapes. So what we're going to do today is we all know some very simple ones. Squares, triangles, and almost everybody is familiar with a cube and how to draw a cube. So what I'm going to do today is I'm going to teach you a few more complicated geometrical shapes. And on the front of the ISW Instructional Skills Workshop page, I actually have a picture of one of the objects we're going to construct today. Can you tell me what these are? You didn't know that was a test to get you to read down there, did you? Yeah. That was my free test, see if you could read. No. Yeah, identifying the symbol of picture pyramids, okay? So what we're going to do is I have equal amount of our building blocks and briefly describe what they are. But they're little magnets, and all of us have been familiar with playing with magnets, and we have little steel balls. And so we're going to construct some basic shapes, and the first shape that we're going to construct is called a tetrahedron. And again, there's another picture, identical to what we saw in the instruction on the front sheet of our booklet. And a tetrahedron, go ahead and separate them. I'll walk you through the steps. We have 4 sides, 6 edges, and 4 vertices. So that's what we're after. And a lot of people have difficulty constructing 3-dimensional geometrical objects in their head. And there's 3 ways to construct this one. I see you guys have already just blasted right on ahead and done it. Maybe it was a little bit too easy, so we'll go through this quickly. All right, so let's see. Lately, you haven't gotten yours going yet. All right, so what I want you to do is to lay out a triangle. That's a basic shape that we're all very familiar with. And so, construct a triangle. You're ahead of the game. You guys are done.
We can deconstruct.
Yeah, okay, so you guys are
This is my second construction. I dismantled it. That's what you saw me.
This is actually the most basic design that you can construct in terms of a 3-dimensional object. All right? And why, let me ask you this, why do you think that's the most basic design in terms of a 3-dimensional object? Why is that?
It's based on a triangle.
Based on a triangle, good.
It's symmetrical.
It's symmetrical, good. What else?
It's stable.
It's stable. Why do you think it's the simplest one?
Fewest sticks.
The fewest sticks or the fewest number of sides that you can create geometrically. Right? And that's why it's a tetrahedron. It's the smallest shaped object you can make because it has the least number of sides that you can construct 3-dimensionally. And so tetrahedron comes from the fact that it's got the 4 sides, and hedron is a crystallized or a geometrical 3-dimensional object. And so here's the 3 methods to construct that, but I see that this is far beyond your skills. So let's move on to a more complicated object, the octahedron. And for those who are familiar with languages, you guys might be, don't start yet, okay? I'm gonna lead you through this step. Don't get ahead of me. All right, so constructing an octahedron, here's kind of my 3-dimensional view. We have up on top here, and this goes down into the board. It's kind of hard to do on paper, and so when you design and write objects on the board in chemistry or physics, or you're trying to describe 3-dimensional objects, it's very hard to do in 2 dimensions. It has 8 sides, hence the octa. It has 12 edges, and it has 6 vertices. So how are we going to go about constructing that? Yeah. You guys are trying to figure it out for yourselves. That's good. This one's a little more complicated, not quite as easy. All right, here we go. Here's what I want you to do. There's two ways to construct it. We're going to go through both the methods here. The first one is to make a triangle, and that consists of 4 consecutive triangles where you start with one on the top, put one flipped over beneath it, and then add 2 to the end. So you end up with 6 marbles there. Good. And once you have that shape, just relax for a sec. Almost. There you go. Stretch the triangle here. There you go. Use another marble. Good. Okay, everybody's got their triangle that looks like this. Okay. Now here's what you're going to do. On the 3 corners of your triangle, just take those marbles and lift them up together. Okay, now don't lift them all the way up. Okay. You see here in the second picture that you just have them lifted up. You just have them lifted up vertical to the table. So yeah, there you go, just kind of like that. And then reach over and grab 3 of the connecting arcs with no marble.
So now we just want to be vertical.
There you go. Now grab 3 more sticks. And bring them in. You've done when you drop the 3 sticks. There you go. Okay, now if you hold it up on its side, you can see there that it is an octahedron. You can go ahead and count the sides and count the edges. And we should have 8 sides, 12 edges, and then how many vertices? Do you remember? 6 vertices, 6 corners. And the marbles are representing the vertices.
Yes.
The black parts are representing the sides.
Okay.
So, and you notice there, if you take half of that, cut it in half, that was the shape of our pyramid that we had earlier. All right, let's try it a different way. Let's construct it using the prism method. So take it apart. Okay, the prism is you take a triangle, make 2 3-sided triangles, and then connect them, stand it up, put one on top of the other, and then use 3 rods between the 2 marbles of your triangles. So, that's right, so make just 2 triangles separately. Good. Take that off. Good. Yeah, then build a tower with a triangle on top of a triangle. Yeah, that's it. You're going to put that one right on top, so then put your little parts in there. There you go. So that shape here we have, there's a prism. Okay, this is kind of a neat way to do it. What we're going to do now is, you see here we have our prism sitting there. Now what you want to do is kind of look at it from the top. You see the triangle and the triangle. What you want to do is twist it so that the triangle points are opposite of each other. But don't let it fall apart. Yeah, it's kind of hard. You're going to need 2 people to kind of do it together. And that's okay if it falls apart a little bit. Once you have that twist into it, just add 3 pieces to the openings there.
So a piece.
There you go. Yeah, exactly. Good.
There. And then I take it and one of those there. Yeah.
Excellent. So there's a lot of different ways to construct geometrical objects. Lakshmi, you're in chemistry.
Yep. What
kind of objects can we identify with the octahedron? What? Carbon, yeah. Carbon's a tetrahedron. I usually think about it in terms of one of the basic crystal lattice structures, and fundamentally, in terms of the way things build together, they take on simple geometrical shapes that involve the triangles and the squares. And so these opposite shapes are really the foundations and building blocks of everything that we do in life. In your child development, the kids start off, they basically learn blocks, squares, circles, triangles, connecting together with sticks. Here I have some pictures of some more complicated objects, and I just want you to see and point out that in all of the objects, they all take on the basic shape and context of triangles and squares, and that really we can have a basis and a foundation to build those up from our basic constructions of these triangles and symbols.
like primary colors in a way. You make secondary and neutral and
Exactly. When you're an artist, some of the basic skills they teach you is how to use the primary objects and basics to draw. I've been a part of introductory drawing classes, and they just say, draw a triangle, draw a circle, and they construct happy faces, clowns, trees, all kinds of different things from the basic shapes. So that's it. I hope you enjoyed, and you learned how to construct a few geometrical objects, and it helped you solidify those in terms of your mind about what those two objects were. What were they, Robert?
tetrahedron, pyramid, prism.
Octahedron. Yeah, it's fun. So.
Okay.